The Seer, a Team Straw Hats production. Sponsored by the Korat Foundation and the Department of Engineering Science at Sonoma State University.
Good morning, everyone, and welcome to Team Straw Hats project presentation and project demonstration. My name is Peelen, and along with my teammates Victor Madrid and Tate Harsch-Hudspeth, we'll be presenting and demonstrating our project, The Seer. Our faculty advisor is Dr. Mohamed Salem, and our industry advisor is Joe Reid. Let's begin with the problem our design system is looking to solve. Direction of arrival, or DOA, is a method of determining the direction of an incoming RF signal propagating from a signal source. In finding the DOA, most common methods do not account for many things like multipath interference and constructive and destructive interference. Signals propagating through non-isotropic environments often follow a nonlinear path and often display non-proportional characteristics in signal strength and attenuation over distance. Modeling this resulting inverse problem to represent a nonlinear environment can be almost impossible.
So the current existing solutions are full dimension MIMO that can easily find the direction of incoming signal, but is very expensive and not precise, triangulation that finds the signal while wasting lots of power, and other alternative models, which are multiple signal classification algorithms, Esprit, Patagram, and SAMV, just to name a few.
Our proposed solution is to implement a system that uses deep learning to determine the direction of arrival of an incoming low-band 5G signal. This system works well in indoor urban areas since the environment need not be isotropic. Our neural network will develop a model that accounts for the complexity as well as the non-isotropic nature of the environment. Our prototype is meant to be a proof of concept and solves the problem by mapping the EM spectrum through training.
Next, we have our comprehensive system diagram. Utilizing a HackRF1 paired with a PortaPack, we broadcast a low-band 5G signal to an array of 3 receiving antennas. Each antenna is attached to a RTL SDR as the received signals are then processed by a Raspberry Pi, saving and sending the processed signals to an external hard drive. A CPU then accesses the external hard drive, training and testing the neural network. Once complete, the neural network makes a prediction of the direction of arrival of the transmitted signal, displaying the result on a graphical user interface. The team will now display the operation of the Seer within our systems test environment.
Hey, how's it going? My name is Victor. Here we are in my garage. As you can see, there's a bunch of stuff, junk, and making it the perfect place to test our neural net.
So here's the setup that we have here in the garage. On the right is the Raspberry Pi 4 interface with the antenna array. On the left, you see there with the 3 antennas. In front is a grid, so we know where in the area we're taking the measurements. Here's the transmitter in front of the antenna array where it's sending a 5G signal to the array, where then it's sent to the Raspberry Pi 4 for processing. Here's the new radio flow graph where it turns the raw data into a binary data file where it's then sent to Tate to be processed.
Thanks, Victor. I've downloaded the binary data files and used our data extraction Python code to target the data of interest and compile it into a CSV file to be fed to the neural network. I will now use the neural network, which has been trained on 100 measurements, to predict the location of the transmitter using the validation data Victor collected. These samples are not part of the training dataset, meaning the neural network has not been exposed to them before. Before team member Evan explains the results displayed by the graphical user interface, take a look at the model summary, which shows 2 hidden layers, each with 32 weights, and a 2-node output layer corresponding to R, theta.
Thank you, Tate. After running the test data points through the Seer's trained neural network, the Seer's graphical user interface is displayed. Both the relative signal strengths and dBW for each of the Seer's 3 receiving antennas are displayed, along with the neural network's predicted distance and angle measurements for each tested data point. Located to the right of the GUI, the predicted distance R and angle theta set for test measurement 1 is displayed on a polar plot showing the predicted direction of arrival of the incident low-band 5G signal. Additionally, located towards the bottom of the Seer's graphical user interface, the average distance difference of 0.65 meters for a total of 10 test data points can be seen, along with an average theta difference of 22 degrees. Located at the bottom of the Seer's GUI, the total system accuracy is displayed. The Seer was able to predict the direction of arrival of the incident low-band 5G signal with a system accuracy of 90%. A system accuracy of 90% speaks to the ability of our deep learning algorithm to build a model representative of our complex non-isotropic test environment. This concludes the Team Straw Hats project demonstration of the Seer.